Hey, Ruby. 你好.
Hi,
How are you?
fine.
Only one here today.
Hmm?
Where are your classmates?
I don't know.
Uh, you're the only ones here today, Ruby and Lynn. And it seems you're the only ones who submitted your assignments yesterday. Um, did you guys have any problem with the work yesterday? No problem. Okay. Let me share my screen now. Okay. We do not have much time to waste. We are supposed to finish up with these things very soon. So we just move ahead, okay? No matter whether other students are coming or not. So today we'll just move ahead and talk about how to resolve forces at other angles. You'll recall from yesterday's class, just a quick recall of yesterday's class. We saw that if you have a force, like so, we can resolve this force into vertical and horizontal components, right? If this angle is theta and this force is say F, then this component will be F cos theta, and that component will be F sine theta, right? That is what we saw yesterday. And we can use this idea to solve many problems like a problem we have in the book. Let me look at a problem in the book. Here is one problem here. In this problem, we are looking for if this object is in equilibrium, we are asked to look for the forces T and R. We know that we can resolve this one this way to get T cos 25, and we can resolve it that way to have T sine 25. And for the R force, we can resolve this way to have R cos 65. And that way we have R sine 65. Then we resolve vertically. We will get R sine 65 plus T sine 25 should be equal to the 10 Newton force. And then we resolve horizontally. We will get R cos 65 is equal to T cos 25. Now, this system, these problems, these equations, equation 1 and equation 2, there are two equations with two unknowns, and we can solve these two equations to get the things we don't know here, right? But it's going to take a bit of work to solve these two equations. It's going to take some time and a lot of work. So in today's class, we are trying to see how we can, in some other problems, an alternative method we can use to solve this problem more easily instead of forming these two equations. So in essence, we will not resolve these forces horizontally and vertically. We can resolve the forces in any two perpendicular directions. So what we are saying is that before we move into that, so if you consider, for example, no, before I talk about that, what we are saying is if you have a force like this, we can choose to resolve vertically and horizontally, but we can also resolve it in some direction that is perpendicular to this force, and another direction that is along this force. And the idea is that the force that is perpendicular to this will always be zero. This component will always be zero. And it will make the problems much simpler. If you guys still do not understand what I'm talking about, you will see in a minute. If you have a force, any force, and any direction, let's say you have this force and you have this direction, the component, if this angle is theta, the component of this force in this direction will always be F cos theta. So generally, you can resolve forces in any direction. And the component of the force in any direction will be the magnitude of the force times the cosine of the angle that the force makes with that direction. So if I have a force here, F, I can find a component of this force in this direction. If this angle is alpha, this force, the component of this force here will be F cos alpha, always F cos alpha. This idea is very important when we start to talk about work. So why is that important? Let's look at this problem here. Let us consider an object that is released from rest on a smooth inclined plane. Let's say that you have a plane, you have this plane, and then you lift it up through some angle, theta. So you lift it up like that. Let me lift it up a little bit higher. You lift it up through this angle. Let's call this angle theta. And now you are told, you will be given a problem in which you will be told something like that there is an object. An object is placed somewhere on this plane. Let's say the plane is very smooth. The object will have to slide down. And you will be asked questions such as, if it is placed here at rest, how much time does it take to move down to the bottom, for instance? If it's placed here at rest, how far does it travel after 2 seconds, for instance? So you have to use Newton's second law and the Stewart equations in this case. So first, you have to think about the forces acting on this object. There is the weight. It is always vertically downwards. The weight, let's just denote the weight mg. And then there is what? There is the normal contact force. Let's call it R. Now, you may be required to find the acceleration of this object down the plane. You'll be required to find the acceleration down the plane. But if you look at these forces, if you try to resolve the forces vertically and horizontally, it's fine. However, vertically and horizontally, the acceleration will not be able, you will not be able to find the acceleration because the acceleration is neither vertical nor horizontal. It's along the plane. So you will have to resolve these forces. One, you will have to resolve along this plane and perpendicular to the plane. Okay, so this is where this is going to be very useful. So you have to resolve the weight perpendicular to the plane and along the plane. Now, if you look here, this angle is theta. So this angle must be 90 minus theta. And this angle is perpendicular to the plane. So this angle is also theta. So the component of the weight perpendicular to the plane is mg cos theta. And therefore, the component of the weight along the plane, this should be mg. Since this angle is 90 minus theta, this one will be mg cosine of 90 minus theta. But the cosine of 90 minus theta is the same as sine theta, so it's mg sine theta. That's the component of the weight along the plane. And this will be the force that will cause the acceleration of the object. Okay? Let's just go straight to the exercises. This is exercise 3D. Exercise 3B, not 3D. 3B. We are asked to find the components of these forces in the direction of the dashed arrow. Although it might not seem clear, it might seem clear from the diagram, make sure you specify whether the component is in the given direction or in the opposite direction. So for this force, the component along this line will be 150 cos 35. For this force, it will be 14 cos 25. And it's in this direction, correct? Because when you resolve like this, it is like a projection of this force on this direction. This one is a projection of this force on that direction. So it is that direction. For this one, for instance, you will have to project the force along this line. So the component of this force will look like this. It will not be that way. And it's going to be 3.5 cosine of 180 minus 161. Now, if you use 3.5 cosine of 161, you are going to get a negative direction to show you that the force is in the reverse direction to this direction. And for this one, you can also use 6.5 cosine of 144, but this will also give you a negative value to tell you that the force is in that direction instead. Okay. Question 3 is a good example to solve on this idea. A particle has 3 forces acting on it, as shown in this diagram. By resolving perpendicular to and parallel to F, find F and theta. Of course, here, it will be possible for you to resolve these forces horizontally and vertically and still look for F and theta. But this will take you much more time and more work to do. So a simple way to do it will be to resolve parallel and perpendicular to F. If we resolve parallel and perpendicular to F, then we can eliminate F. So we will have one equation with one unknown. Because the component of the force that will be perpendicular to F will be the component of F that will be perpendicular to F will be 0. So in this case, we can have this force will have a component this way. We can look for this angle. This angle should be 40, right? So this will be 10 cos 40. It will have a component that is perpendicular to F. And you can find this angle. This angle will be 50. So this will be 10 cos 50. And the 8 Newton force, you can also resolve it parallel to F. Let me use a different color for that. You resolve the 8 Newton force parallel to F, you will have 8 cos theta. And then you also resolve the 8 Newton force perpendicular to F. This angle is theta and this is 90 degrees. So this will be 90 minus theta. So this will be 8 cos 90 minus theta. But cos 90 minus theta is sine theta. So it's 8 sine theta. You can now see, since this system is in equilibrium. The system is in equilibrium. It means in any direction, on any line, the sum of forces will be 0. All right, so we, instead of resolving vertically and horizontally, now we will resolve first perpendicular to F. We'll resolve perpendicular to F. First perpendicular, we will have this force should be equal to that force. So you have 8 sine theta should be equal to 10 cos 50. Now you see, you only have one equation with one thing that you don't know, so you can easily solve for theta now. That gives us sine theta to be 5/4 cos 50. And so theta will be sine inverse of 5/4 cos 50. What is 5/4 cos 50? Let me use my calculator. First, make sure my calculator is in degrees. Yeah, it's in degrees. And then I'm looking for sine inverse of 5/4 cos 50. That gives me 53.464. 53.464. 53.464 degrees. So in A-level requirement, you will give the angle to 1 decimal place if you are not told. 53.5 degrees. Next, we have to resolve parallel to F. We apply Newton's second law along this line. So we will have what? We'll have 10 cos 40. So 10 cos 40 should be equal to 8 cos theta. 8 cos theta plus F. Right? So now our F, what did I do? What am I doing here? So now our F should be 10 cos 40 minus 8 cosine of theta. We already have theta. Now, one interesting thing, why did I first give this value to more decimal places? Because I knew I'm going to use it next. So I should use this one that is more accurate or more precise than this one, huh? If I use this one, I'll get a more accurate value. So this will be 8 cos 53.464. So I can calculate that, which I don't think I should spend time doing that. Anyway, what we are saying is that if you have a problem to solve like this one, you can choose to resolve parallel and perpendicular to one of the forces. And it's going to eliminate the effect of that force in the perpendicular direction. And so you will reduce the effort you should use on this problem, all right? The next problem is that my favorite problem, which is a book of mass 3 kilograms is prevented from sliding down a slope at 15 degrees. That is my favorite problem. So we have a slope and it is inclined at 15 degrees. And we are told that there is a book on this slope. Let me use black for the book. And the book is prevented from sliding down by friction acting up the slope and parallel to it. There is a frictional force acting up the slope and is parallel to the slope. This friction, let's call it F. We are asked to find the frictional force and the normal contact force. This is a typical problem you would have in an exam. So we have the friction. First, you think about your weight always acting vertically down. You are told the mass of the book, so the weight will be 30 newtons. You are told there is a normal contact force. You are not even told, you should know there is a normal contact force and it is always perpendicular to the slope. The normal contact force is R. So what we should do here is simply to resolve the weight. In this inclined plane problem, it is almost always the weight that is resolved. And this component is always going to be 30 cos, that angle cos 15. And this component will be 30 sine 15. From here, we are done. We can resolve first parallel to the slope. We look at parallel to the slope. Since the book is not sliding down, it means the frictional force must be equal to this component of weight. So we'll have F equal 30 sine 15. Next, we resolve perpendicular to the slope. Perpendicular to the slope. Since it is not accelerating perpendicular, it means R must be equal to 30 cos 15. So that R equal 30 cos 15. You see how easy this problem is solved. If you had to go by resolving horizontally and vertically, it would take you ages to find F and R. It would take you at least 3 hours to work on it if you are a slow student. Not that it's impossible. It's possible to resolve horizontally and vertically and get it, but it would take you a very, very, very long time. Understand? That is it. Maybe I should solve one more problem. Is Floria there? Floria is not there. Anna Jung. Anna, you didn't submit your homework yesterday. Maybe I should solve one more problem, just one more. This end of chapter exercise on friction. Forces in 2 dimensions. These are own forces at other angles. You see, there are many forces, many problems on that inclined plane thing. I'll leave it for you guys to practice. Here is another one. It has to do with something here. Let me look at this one and see what it says. We are told that a girl is dragging a sled of mass 20 kilograms up a slope at an angle of 14 degrees to the horizontal. She pulls at an angle of theta above the slope with a force of 30 newtons. She maintains a constant speed despite friction of 10 newtons parallel to the slope. You are asked to find theta. So the angle is theta. She's dragging a sled of mass 20 newtons, 20 kilograms. So the weight is 200 newtons. And we are told that she's dragging this sled at an angle of 14 degrees to the horizontal. So she's dragging at some angle like this. No, the problem says this angle is 14 degrees. This angle is 14. And she is dragging at some angle theta above the slope. So she's dragging at an angle of theta above the slope. And she's pulling with a force of 70 newtons. We are asked to find theta and the normal contact force. So you simply resolve your weight. Your weight will have a component this way, which is 200 cos 14. It will have a component this way, which is 200 sine 14. I left out one force. There is the normal contact force. And we can now resolve this 70 Newton force parallel to the slope. You will have 70 cos theta. We resolve perpendicular to the slope, we'll have 70 sine theta. And so now we resolve first, I'll resolve parallel to the slope. Parallel to the slope, I will have this force should be equal to that. 70 cos theta should be equal to 200 sine 14. That will give you cos theta to be something. You can calculate that. Second, I will resolve perpendicular to the slope. Then I will have the normal contact force plus 70 sine theta should be equal to 200 cos 14. And since you already have theta here, you can solve for r here. Okay.
I think the friction is down the slope.
Very, very, very good. There is a frictional force of 10 newtons. Who is that? Who was that, please?
Lin.
Lin. Thank you. There's a frictional force of 10 newtons acting down the slope. So this one should have 70 cos theta should be equal to that plus 10. All right. Thank you very much for the correction. Sometimes it's very easy to miss out these things. You know. Okay. Our time is up in 2 minutes. So if you have any questions now, you can ask me. If no question, then you will go to, I have a new course built. You look at the new course and you will study lesson 1 and lesson 2, complete lesson 2 today. There are some videos there for you to watch, and your homework is also there. Okay. Thank you guys for coming. Anna Jung. Anna. She's not there, right? I will mark you absent for this class. I've called you several times to do an answer. Because I think sometimes a student can just sign in and then just leave, you know. So I see that they are here, but they're actually not here. Okay. Okay, see you guys. Have a good weekend.
Bye bye.